This video is going to serve as an introduction to the Jasco FP750 spectral fluorometer. In this case, we're going to be using the instrument to determine quantitatively the amount of quinine in a sample of tonic water. So I'm not going to go through the whole experiment, but I will show you the basic setup and operation steps required to use the instrument. So first off, a quick tour of the instrument itself. The Jasco FP750, as I mentioned, is a spectral fluorimeter. So its purpose is to measure the amount of light that is emitted from a fluorescent sample, such as quinine. So to do this, we have to have a xenon arc lamp, which is a broadband continuous source, which is hidden right back here. And then just under that, which we can't see here, is a monochromator. And that monochromator is considered to be the excitation monochromator. So that monochromator will be tuned to a specific wavelength of interest from the xenon arc lamp. Alternatively, we can use that monochromator to scan a range of wavelengths from the xenon arc lamp. Then, off to the right of the sample container or compartment, which you see here, and we see a sample cuvette in there right now that now contains a 1 part per million standard sample of quinine. To the right of that, we'll have a secondary monochromator, which we call the emission monochromator. So it would be housed in this region here. And what the emission monochromator does is it picks off a specific wavelength or range of wavelengths of light that are actually being emitted from the fluorescent sample itself, which in this case is going to be quinine. And then above that would be a detector up in this region here, most likely something sensitive like a photomultiplier tube. Alright, the only other thing to know about the instrument, I can't show it to you here, is that the on-off switch is on the left rear panel, and you'll feel it right there. Alright, so for the moment I'm going to close the sample compartment and we'll walk over to the computer. So the primary thing to remember is once the computer is fired up, before we enter the Spectral Manager software, the icon which we see there in the lower left, we have to be certain that the instrument has been turned on and presumably has a little bit of time to warm up. So I'm going to go ahead and move into the software. So again, we want the Spectral Manager software here. And what we'll find is that we move into a menu option here. And we have an option between two instruments here. So I can toggle here between the FTIR, which is the instrument here to the right, and the spectral fluorimeter. So I want to make sure that I'm choosing the FP750 option here. So that means we'll be addressing the spectral fluorimeter as opposed to the Fourier transform infrared spectrophotometer. Alright, so following through in a basic sense, presumably at this point you have generated a series of standards and you have a quinine sample from tonic water prepared and ready to go. So once this is finished, we can go ahead and start to access the instrument. So the first thing we're going to want to do is to acquire two spectra. We want to determine the wavelength of interest over which the quinine will absorb light, and then the wavelengths of interest over which quinine will emit light. So we have to get what's called an excitation spectrum, and then we also have to obtain what's called an emission spectrum. Alright, so that said, we want to begin in the spectrum measurement option. So I'm going to double click that. Alright, so the appropriate information is being transferred from the computer and the software over to the instrument so the two can communicate with one another. So we'll give that a moment or two to happen. Now the information is being transferred. And it looks like we are in. Alright, so at this point, we have to actually set the experiment up. So according to the information given in the instructions, we need to get into the measurement option, and from there we want to go to the parameters. So we'll click on parameters. And this is going to give us a menu of different parameters that we can choose for both emission and excitation. So I would like to start by scanning an excitation spectrum. So I'm going to go to the top box here, and I'm going to scroll up a little bit. So notice that that first option was hidden, and I want to choose excitation. I'm trying to generate an excitation spectrum. We're going to leave the excitation bandwidth at 5 nanometers. The emission bandwidth, these all refer to the slit settings on the monochromator, will also be 5 nanometers. We'll be looking at a fast response. The emission wavelength is just a general wavelength where we know that the sample will emit. It may not be the optimal wavelength, we just need to be at a wavelength somewhere where we know that the sample will emit radiation. And 450 nanometers will do the job there. The other thing we need to do is to set the range for excitation. So the excitation is going to be down in the ultraviolet part of the spectrum. So we are going to scan between 220 nanometers and 400 nanometers. So my start wavelength will be 220, and we'll start right at the cusp of the visible region at 400. The data pitch will be 1 nanometer. That's referring to the resolution of the spectrum. And the scanning speed will be at 125 nanometers per minute, and the sensitivity will be set at low. All right, so now that we've done this, we can go ahead and acquire the spectrum. But before we acquire the spectrum, we need to actually open the shutters that protect the sample from the radiation coming from the xenon arc lamp, because samples can actually photodegrade. So we need to sort of open the doors so the light can come in. So I'm going to go ahead and OK this and transfer the parameters. And now I'm going to open the excitation shutter, and I'm also going to open the emission shutter. So now light can move from the xenon arc lamp through both monochromators and the sample and ultimately to the detector. All right, so now we're ready to actually start acquiring the spectrum. So I'll hit the start button here, and we will actually see the spectrum beginning to start. So what we see here is that we're getting an intensity here in terms of detector counts as a function of wavelength. So this is actually, in a sense, light being emitted, but we're tracking that light only at a specific wavelength of emission. So we're seeing what effect the wavelength coming from the source has on that. All right, so we're actually getting something that's more or less like an absorption spectrum, but it's actually presented here in terms of emission counts. But the meaning is essentially the same. This is essentially an absorbance spectrum. It's showing us where the quinine actually absorbs the most light. And what we're seeing here is essentially that we get 2 maxima here. You can see a maximum up there near 250 nanometers, and it looks like we're getting a second maximum out around 350 nanometers. And we're going to be able to actually record both of those here momentarily once the spectrum has stopped acquiring. Okay, so the spectrum has stopped, and now what we've gone into automatically is what's called a spectral analysis mode here. And this allows us to actually annotate the spectrum and analyze it. So notice that I have a red bar here which I can drag. Now the red bar, notice as I move it, is allowing me to track wavelength and intensity as I do so. So I'm going to center the red bar on that first maximum, or somewhere close to it. So we'll take that wavelength right there. And what we see here is that that wavelength corresponds to 253 nanometers. So I'm going to write that down because I'm going to need that a little bit later. Okay. Now I'm going to look also at the second maximum here. So I can either drag the bar, or I can click and then drag and try to find that next maximum. And I have it somewhere around, in this case, 351 nanometers. So I'm going to write down that value as well. The reason why we're doing this is we're going to generate actually two standard curves. We're going to generate one standard curve for the maximum that occurs at shorter wavelength, and then we're going to generate a second standard curve using the maximum that is generated at a longer wavelength. Okay, so this is the excitation spectrum. So we want to then move out of that mode. We don't need to save this. If you do want to save it, you can certainly do that. I'm not going to save it in this case. And I'm going to move out of spectral analysis, and I'm going to go back into the spectrum measurement mode here. Okay, so that's automatically there after we close out of the spectral analysis. All right, so now I'm going to go back into measurement because what I need to do is acquire a second spectrum, which is going to be the emission spectrum. So what I want to do here is to open up the parameters. And at this point, I want to move out of excitation and into emission. And I'm going to leave the bandwidths the same. All those parameters are going to remain the same. And I'm going to leave my excitation wavelength at 253 nanometers. That was my short wavelength maximum that I found from my excitation spectrum. So I know that I can use that wavelength of light to cause emission of the sample to occur. So we'll go ahead and use that. Now, since I'm looking at emission now, I need to change my wavelength range. Because as we may remember from class, or from your reading of the packet, the emission spectrum is always going to occur at a longer wavelength than excitation will. So if excitation occurred in the UV, we might expect emission to occur in the visible part of the spectrum. So I'm going to start where we left off, which will be 400 nanometers, right at the front end of the visible part of the spectrum. And I'm going to end at 650 nanometers, which takes me close to the red region of the spectrum. We're going to leave all the other parameters the same, and we'll say OK here. All right, so we're transferring our parameters here. OK. And notice that the shutters for excitation and emission remain open. And at this point, we are going to go ahead and start in order to obtain that emission spectrum. So again, we're looking at counts at the detector on the y-axis as a function of wavelength on the x-axis. Okay, so we'll stand back and watch the spectrum generate. This one occurs a little bit more slowly, I believe. But we can see that we're approaching a maximum here. Looks like we may have just cut the top of it off, but that's all right. Now, if I were worried about that, what I could have done was I could have chosen my other excitation maximum, which was out around 350 nanometers, and that would actually lessen the number of counts if I wanted to catch that last little bit there. So that might have been the better thing to do, and in fact, if you want to do that, you certainly may. And that way you'll see the entire spectrum. But we'll go with this for the moment. It should be fine. The alternative thing we could have done there is used a lower concentration sample as well. Something a little lower than the 1 part per million. That would have also reduced the counts. Almost finished here. So as this finishes out, we'll automatically move to the spectral analysis mode where we can do annotation and observation of the spectrum. Here we are. And we see that we also have our red bar here, which I can move to some place around the maximum. So we'll assume the maximum occurs somewhere in the center of the flattened region there. So again, I can come down here and track that. And it looks like I'm at around a wavelength of 464 nanometers. So I'm going to write that down. course, your results may vary a little bit, so you don't necessarily want to take my numbers to the bank. All right, so now we can leave the spectral analysis mode here because we've actually acquired our wavelengths, optimal wavelengths for both excitation and emission. Okay, so again, we'll leave spectral analysis. We'll go ahead and leave spectrum measurement and go back to the main menu here. Now, at this point, what we want to do, and excuse the message there, at this point, what we want to do is to move to the fixed wavelength measurement mode. For fixed wavelength, this means we're going to be sitting at one specific wavelength for excitation for optimal results and one specific wavelength for emission, also for optimal results. Okay, so if you recall, we have two excitation wavelengths we can use and one emission wavelength that we can use. So I'll double click on fixed wavelength measurement. Again, we're transferring parameters here. Okay, now if I come back to the menu that's underneath, I'll click on that to bring it up front. And again, we want to take a look at our measurement parameters here. So we're going to go back to parameters. And I believe here we're going to use the default parameters. We're going to keep our excitation bandwidth at 10 nanometers, our emission bandwidth at 5 nanometers. We're going to allow our response to be 1/10 of a second, and the sensitivity will remain low. Okay, so the thing that we need to keep in mind here is that we have to choose both an excitation and an emission wavelength. So I'm going to leave the emission wavelength at 464 nanometers. I believe that was the value that I wrote down. But remember, I had two excitation values here. So my first excitation value is 253, so I'm going to go ahead and change that value to 253. Okay, and I'm going to say OK here. Transfer those parameters. All right, so at this point, you would go ahead and load into your sample compartment your blank. And you could acquire now counts for your blank using those wavelengths. Okay, so let's just go ahead and hit start here. I'm using actually the 1 part per million standard here because that's what I've got in the sample compartment. All right, so there we are. We're getting actually a response of 188.26 counts for that 1 part per million sample. So that's something you would want to write down because that becomes a data point in your standard curve. Now keep in mind that we also have the other excitation wavelength. So I'd like to be able to get two standard curves, so I need to have the data point for the other sample, or rather the other excitation wavelength. Now that one I believe was out at 351 nanometers, so I'm going to go ahead and change this to 351 nanometers. All right, so I'll say OK here. We're transferring the parameters. And now I'm going to acquire the counts for that secondary wavelength. Okay, so there we are. So in this case, I get 68.41 counts. Now this sort of makes sense when you think about it because that second maximum was at a much lower intensity than the first maximum. So as a result, we're going to see more excitation occurring, which translates to a greater emission at the shorter wavelength. Okay, so that's why we see the variations there that we're seeing. So now we have a data point each for two different standard curves. So again, you're going to generate a standard curve using intensity acquired at 253 nanometers as a function of concentration, and then another standard curve where you're going to be plotting the counts that you get at 351 nanometers also as a function of your concentration of your quinine. All right, so in this case, you can go ahead now and acquire all of the different standards that you need to generate the standard curve, And then also you can acquire the data that you need for the quinine sample from the tonic water, and then apply the standard curve, or rather both standard curves, to determine the quinine concentration. All right, the one final thing to show you here is, now that we have both shutters open, you can actually see the blue light being emitted from the sample there. And that's the actual emission of the light from the fluorescent quinine in the tonic water. So again, you can't see the excitation light because it's in the ultraviolet part of the spectrum, but you can see the emitted blue light from the fluorescing quinine from the tonic water. All right, so hopefully this has been a good introduction to the Jasco FP750 spectrophlorometer.